All right, so welcome to this is like the pinnacle, right? Because we talked about Legos. You have built the base, and honestly, Calc 1 and Calc 2 they're pretty cool things. But we learn these things, and we never get to use them to their full potential and see what they can really do for us. Calc 3 doesn't do all of that, but it gives us a really good insight into why you learned a lot of the Calc 1 and the Calc 2 stuff that you just did, like integration techniques. Like, oh, okay, fantastic, what we're doing, I don't know, area under a curve or something like that. Yeah, that's right. But we can use it for a lot more stuff. And how we get to that more stuff right now, the next level of our base. So, I mean, we built with Calc 1, we built with Calc 2. Now we have this kind of like RAM part we're working on called vectors. We're going to learn about vectors so that we can come back and flesh out all of the rest of Calculus 3. Why we need vectors. Number one, it's really hard to describe motion in 3 dimensions if you don't have them. So vectors allows us to do that. Also, even in 2 dimension, sometimes, I mean, not sometimes, a lot of the times, just a speed or just a direction isn't good enough for it. For instance, if we're driving down the freeway, go, hey, where'd you go? 60 miles an hour. What are you talking about? I mean, where did you go? I was going 60. Great. 60 where? 60 north, 60 south. That's going to make a difference where you end up in Sacramento after a couple hours or Los Angeles is going to make a difference. So we don't like to just describe direction. We don't like to just describe speed. We like both. We want to say we were going north. We were also traveling at a speed, a magnitude of 60 miles an hour. Or we were going east and we were going 30. Or we changed direction in somewhere. We got a couple vectors going on. That's the idea. That's why we have this vector idea. Now, when we talk about vectors, if this is your first time ever seeing vectors, I'm going to try to break it down to show you what we're talking about here. Is it anybody's first time seeing vectors? Okay, that's good. You can be honest in this class. Yeah, how many people first time they ever heard of or seen a vector before? Show of hands if you never. That's a few of us. Here's what vectors have. Vectors are this way to describe motion, way to describe a particle, way to describe even a function later on, that give us both a speed and a direction. The speed, I want to talk about that a little bit more. When we talk about speed, that's not really great because sometimes we don't have speed with all of our vectors. Sometimes we have this different connotation with it. Instead of talking about speed a lot, we're going to call this thing magnitude. So if you want to talk about something having a more speed, more force, we're going to call that a magnitude. So when you think speed, think magnitude. Now the direction is something that we usually show on like the XY axis. So it's really similar to drawing like a line segment. So you go, hey, can you make a line segment from the point 2,1 to the point 5,4? Yeah, of course I can. Well, that gives you a direction, right? And if we have the length of that segment, that gives you a magnitude, that gives you a speed. That's really what a vector does. It shows you how to get from point to point, and the longer that vector is, the larger the magnitude, or the faster we got there. That's really what's going on. So what I'm saying here is that the direction is given to us on like an XY plane, or when we get to 3D, an XYZ plane. So this direction is always mapped for us on a coordinate system. One little side note right here, the magnitude. Longer vectors have more magnitude. So what I want you to write, just a little side note, say the magnitude is given by the length of the vector. So when we talk about magnitude, this thing right here is given by the length of the vector. Let's do a couple. So suppose we have this, we're on a plane right now, we're 2D still. So suppose we have a point A, and we have this vector, we have this thing, this car, if you will, this way to travel that takes us from A to B. In the real world, it matters where you start and where you stop. You don't just go, we traveled A and B, done. Well, it matters. Did you start at A? Did you start at B? Did you go from A to B or from B to A? That matters in the real world. It matters to us also. So we always give these things a direction. If we start at A and we end up at B, there was a direction to that. It had a heading. It started at A, we had this arrow pointing to B. And we can define this. Usually what we're going to do in this class, we're going to use V, W, U, A, and B to represent vectors. So we can say, well, we can represent this idea of traveling from A to B by a vector. Here's how we're going to write vectors in our class. Write the letter V and then put this half arrow on top of it. That represents the vector V. And then we can describe the vector V. The vector V is this vector that goes from A to B. The direction matters, like that. If we had to do another one, how would you describe, just for fun, see if you're picking it up, how would you describe that vector? Left side people, you guys, where's that vector start at? Perfect. Right side, where's the vector end at? If I had to write this as, and I do, I have to give it a different name, so vector W, how would I write it? Would I write it CD or DC? What do you think? CD. Yeah, perfect. You guys have the idea. And we're saying that's the vector from C to D. Show of hands if you feel okay with our vector so far. Pretty easy. It's just, it's a vector that gives us a direction and a magnitude. Obviously we covered, well, we're pretty close, but this one looks a little bit longer. We'd say that has more magnitude because it has more length to it. Are y'all with me on this so far? Okay, cool. You know, we can do some math with it too. But we can start doing things like multiplying vectors by scalars. The idea of a scalar is this thing that's just a number, like just a speed. So if you said, I want to multiply by 60 miles an hour, you can actually do that. Increase your speed 60 times, 60 miles an hour. We can increase it by a scalar factor, not a vector. It's just this unit, this number that doesn't have a direction to it. So we can do things like this as well. Let me describe for you a scalar. So we can multiply by constants. This constant for us is called a scalar. Here's what the scalars can do for you. All the scalars can do are these two things. They can alter the length of your vector, or they can reverse it. And we'll talk about, I want you to think about why though. I don't want to just give it to you. I want you to think about why they can't move it, but why they could maybe reverse the direction. So let me write that down and then we'll talk about it. So these scalars can do two things. They can change the length of your vector, quickly, what's the other word for length of a vector? What is that called? Magnitude. So change the magnitude. Or they can reverse.
Are they always constant?
Scalars are constants, yes. Now, I'm going to contradict myself later on when we talk about a scalar function. A scalar function is later on, all right? It's a ways. A scalar function is something that you plug a number into and you get just a number out, though. It's called a scalar function. So when I'm talking about scalar, yes, the thing you get out is a constant and it's a number. That's what I'm talking about. Basically what I'm trying to say. It's not a vector. It's just a number. That's what I'm trying to say. So we can change the length of the vector, we can change the magnitude of a vector with a scalar, and we can also reverse the direction of the vector. Let's try some, because we haven't really done a whole lot here. Let's see how a scalar would work at affecting some of these vectors. So let's do a vector v. I'm going to just make one off the top of my head here, this one. So here's a vector. I don't care where it starts, I don't care where it stops. All I know is that on this plane, it's going this way, and it has a magnitude that says that. Now, what would the idea be if I said, you know what, I want to now find 3 times that vector. So notice what we got. 3 is the scalar here. I'm just multiplying by 3. What's it going to do? Is it going to shift this vector to go more up or more down or sideways? No. All it's going to do is grow this vector. Does that make sense to you? So 3 times the vector v, that scalar's 3. It's saying, hey, I want the same exact direction, but I want it to be 3 times longer. That's the idea here. Does that make sense to you? So I'm going to try to make something the same direction, but 1, 2, 3 times longer. That's the idea of what a scalar does. Now here's my next question. How could that happen? If I said you can't change direction, what I mean is that we can't start shifting this vector any, but I said that we can reverse it. How might you do that? What do you think, Drew?
By using a negative scalar?
How about a negative? A negative says, you know what? Hey, just like going down the freeway, if you went in the negative direction, you're going backwards. So if we start at Merced and we go up to Sacramento, that's a vector. Kind of, well, it's not because it's not straight, but let's just pretend it was. If we did that and we wanted to come backwards, we'd be going in the opposite direction. Opposite of math is negative. Same thing here. So when I want to talk about a negative vector, all it's doing is taking the same exact magnitude and the same exact direction and it's going backwards. We can even do this with fractions. Bless you. If I wanted to do like negative 3/4 the vector v, what's that going to do? Right-siders, what's that going to do? Tell me what it's going to do. Is it going to lengthen the vector, shorten the vector, or leave it the same? Sure. Is it going to be going the same direction this way or direction this way? What's direction? Going upwards or going downwards? Yeah. So is it going to shift it to kind of make it more rotatey at all? That's a trademark word. Here we go. So it's not going to rotate at all. It's going to have the same thing. It's going to be this, but it's going to be 3/4 of the length. That's what's going to happen. And of course, we're not on an XY plane right now, but we're just kind of getting the ideas down. So in your head right now, I need you to have the idea that a vector really describes 2 things. It describes a direction, and it gives us a length. We call that a magnitude. Head nod if you're with me on that. Okay. The next thing I want you to understand is that we can multiply those vectors really simply by these things called scalars. They're just numbers, and they only affect 2 things. Whether we're going in the same orientation or reverse orientation, and then the length of that vector. Are you with me on that one? Where we're going in the future with this. In the future, we're going to talk about something called a unit vector shortly. A unit vector is going to have a length of 1. It's going to give us a direction, and from that unit vector, we can grow any vector that has the same direction by just multiplying some numbers. Think about that for a second. Is that making sense to you? If I say that we can grow vectors, I start with a vector of unit length 1, and say, hey, it's the same direction, let's just grow it. We start multiplying. Or we shrink it, we multiply by fractions. We're going to be doing that in a little while. It's going to make sense. Right now I'm just kind of getting your heads going. Next thing, we're going to talk about, of course, true, false. If I've drawn them correctly. Are these vectors parallel? What do you think? This one looks a little funky, but let's pretend I didn't kind of funk it up a little bit. Will they, if I were to continue them, like forever, would they ever intersect? There's a big theorem about this. It's not a hard one, it's kind of intuitive. Here's what I need you to know. Scalar multiples of vectors are always parallel. Always. It's the same direction. How could they possibly intersect? Same direction, even reverse. Same direction, just reverse direction. How can they possibly intersect? They can't. So when I start taking these vectors and multiplying them by scalars, we always get parallel vectors. Show of hands if you understand that concept. Okay, so scalar multiples of vectors are all, write that down for me. Scalar multiples are parallel. All right, well, hey, we learned a couple things. We know what vectors do. They give us a direction, they give us a magnitude. We know we can multiply them by scalars. That grows our vectors or reverses the direction or both sometimes. But there's some other things we can do. We're going to start talking about, well, what if we're not multiplying? What if we're adding? Can we add vectors? Can we subtract vectors? And the answers are, yeah, we can. And honestly, it's not that hard to do. So I'm going to show you, like, graphically how we're going to add, subtract vectors. It's not hard. I'm not going to spend a whole lot of time on it because I want to more get to as soon as I can, how we do it with actual points, because I want to put the stuff on a graph and see what happens. You guys with me?
Yeah.
Having fun yet?
Oh, yeah.
Have you learned anything yet?
Yes.
So let's see how to add and subtract vectors. How we add vectors, let's say I give you a couple of them. I'm going to give you V and W. Here's our concept for adding vectors. Honestly, not that hard to do, but you do have to know what's going on. When we add vectors together, the idea is we're going to take one vector. So if I wanted to find like V plus W, you literally do this. You take one vector, you move it so that the initial point of your second vector ends up at the terminal point of your first vector. So we want to just match these things up basically end to end. So do you guys understand what I'm talking about? Initial point, terminal point, where we start to our initial point, where we end our terminal point. So when we say we want to add these vectors, really it's literally doing this. It's saying, hey, take that vector V. Draw it as close as you can. We're not going to be perfect here. Take the vector W. Hey, just move it. Just put it right there. So take that vector W.
So
and you
order
go.
matters?
We're going to talk about that in a second. Does it matter? We're going to talk about that. Think about it though. See if you can do it a different way. See if you get the same thing. But here's our answer. Maybe this is going to answer your question here. Here's what the addition gives us. The addition is not just this and this. The addition says, well, what would happen? What would happen if you were on the freeway or going just on a plane and you started here and you went to here and then you went to here? Let's pretend that you could drive like through anywhere that you wanted to, which I try to do. I have a 4-wheel drive truck. So let's pretend I didn't have to do this. I go just right from here. Well, all this is really doing is taking me from here to here, and then again from here to here. Essentially, I'm ending up going from here to here. That's what vector addition does. So this right here, this resultant vector, this is V plus W. That's what that idea is. Quick hit, if you're okay with that one. So basically put them end to end and draw from the initial point of your first vector to the terminal point of your second vector. And you can extend the concept. Now I want to answer the question here. Does the order matter? What do you think? What if you did, let's try it. What if you did W, let's put W down here. What if you did W first and then you did V? Do I end up getting the same exact thing? Order doesn't matter. Yeah. The parallelogram law says that, hey, it's a parallelogram. No matter how you make that parallelogram, whether you go up and over and up, you're going to end up going diagonally from here to here. Either way, you're going to get the same thing. Head down if you're okay with that one. So it doesn't matter how we add it. It doesn't matter at all. Now, what about this one? What if we took and we did v minus w? Man, adding things was pretty easy. You just put them end to end, right? Well, here's how I'd like you to think about how to subtract vectors. Instead of just going directly for the subtraction, this is the easiest way to wrap our heads around it. So instead of this, oops, maybe we use that like basic algebra stuff, like pre-algebra. Instead of subtracting, can you add the opposite? We can do that with any number. These are vectors, and it still works for us. So instead of just subtracting vectors, think adding the opposite. And what that allows you to do is put these vectors end to end and still make sense of it. Because subtracting, it's really hard to think about, well, how would you subtract a vector from one another? But I can add vectors pretty easily. Just put them end to end. Are you guys getting what I'm talking about here? So let's try it. Okay, well, vector v would still look like, give it to me like that. Here's vector v. Vector w, now vector w looks like this. I'm going to draw it back up here so don't get lost with me, okay? If this is vector w, hey, what's negative w going to give you? Can we do negative w? It's going to do the same magnitude, opposite direction. This would be negative w. Show of hands if you understand what I'm talking about. You guys over here, yes, no? So we go, okay, hey, here's v, no problem. If I want to subtract w, no, don't just subtract w. Add the opposite. Add the reverse direction of it. If I do, well, that's something I can put end to end. You see, our vector addition works real nice because I can put my vectors end to end and just go from initial point, like ultimate initial point, to ultimate terminal point and be done. That's what I want to do. Well, here's my initial point. If I put my negative w, I'm going to draw a black pen here so you can see the difference. Notice how the vectors match up. The vectors now go, okay, well, here's my initial point. I'm going from here to here, now to here. Does that make sense? Can you make, on your own paper, try this right now, go from the ultimate initial point, like the starting initial point, to the final terminal point. Can you guys do that? Did you end up with a vector that started here and ended here? This right here is v minus w. And that's how we find it. Don't go straight for the subtraction. It's too hard. It's too hard to think about. So when you're doing the subtraction of vectors, do add the opposite, flip that vector around, you go opposite direction, and we got it. I'd like a show of hands to see if you're okay with what we're talking about. Have I explained vectors well enough for you guys to understand the concept? So the three big ideas we have so far are, there's these things called vectors. They have a direction and they have a length called a magnitude. We can mess with that. We can mess with the length by using scalars. Multiply by numbers. It's going to grow or shrink that vector. Anytime we do that, though, please listen. Anytime we do that, though, multiply by number, we still have something that is parallel. It's the same exact direction. Are you with me on what I'm talking about? We can go a step further. We can start adding vectors. It's not hard to do graphically. You just take one vector, put it at the terminal point of the previous vector, and you can add them. It doesn't even matter the order. Subtraction would. Right? Subtraction would. If you straight up did subtraction and reversed them, that'd be a problem. That's also why we think about negative vectors, because now it doesn't matter anymore. Does that make sense? So when they're trying to subtract vectors, adding is pretty easy. Just put them end to end. You can put them in the correct order. Go from initial point to terminal point, and you create a new vector. Subtraction, just flip it around. Flip the script on it, if you will. Just change subtraction to adding a negative. Flip one of the original vectors, put them end to end, and you can still do it. I feel like I'm over talking it. If you guys get it, we're going to move on. You guys get it? All right, let's do it. you have any questions at all about the idea of a scalar multiplying or adding vectors? All right, sweet. What if we had this special case? What if we had this vector that had an initial point? So all of our vectors have an initial point. They got to start somewhere. That's our initial point. And they got to end somewhere. That's our terminal point. They don't go forever, right? They're not lines. They're not even really rays. They have a starting spot. They have an ending spot. The starting spot's called the what? The ending point's called the what? So what if we have this special case where we get this vector, and its initial point is the origin, and it's got a terminal point at, I don't care, it's just got a point. You're going to see this a lot, just so you know. A lot of times when we're working with vectors, and I'm going to give you the notation. You're going to have to kind of hang out for a little bit. I'm going to give you the notation in a little while. A lot of times when we're working with vectors, we have these components, and we have this terminal point, and we typically use whatever letter we've defined our vector as. We use some subscripts on that letter. Notice there's no vector here. This is a literal point. Like on an xy plane, you'd be able to go to v1 over on the x-axis and then up v2, and you'd be at a point. Do you guys get the point on this? We're trying to take this idea and now put it on an xy plane. So the idea is, okay, so what if you had this vector and it started at the origin? Well, they've got to start somewhere. Let's put it on the origin. And it ends at this point that is an actual point. Like it ends somewhere. Do you guys get the idea on this? Whenever that happens, whenever we get this vector that starts at the origin and obviously ends, we're going to call that a position vector. Position vectors are where we make our money in this class. We talk about position vectors like all the time. Why? Because it's really nice. We always like our vectors starting at the origin if we can, because they're easy to work with. Are you getting the idea here? They're easy to work with. Do they have to start at the origin? No, but we want them to because they're easy. So suppose we have a vector with its initial point, it starts at the origin, and a terminal point at some other point. This specific situation is called a position function. That's what we want. That's what we want. What did I say? Did I say position function? I did say that. I'm sorry. I'm about 3 chapters ahead of where. Position vector. We will be talking about position functions in chapter 13, I think. So we're going to get there. I misspoke here. Position vector. Vector. Let's see. Vector. Here's a question for you. How many vectors could start at the origin? How many unique vectors could start at the origin and end at that point? That specific point. Start at the origin. Have an initial point at the origin and end there. How many? Solamente uno. Rosetta Stone's paying off, by the way. I think that means only one. One. If I say, hey, here's an XY plane, here's the origin, get to that point. How many ways can you do it? Well, you can't do this. One vector does that. So this is called the position vector of this point, because it's literally, there's only one that does that goes from the origin to every unique point. That means we have this like one-to-one relationship between points and position vectors. here it is. It's the first thing y'all are going to screw up. The notation. When we talk about position vectors, we're going to have a different notation for it. Here's how it looks. If we're talking about a position vector, we use these brackets. They look like the greater than and the less than symbols, look just like it. They don't have this, okay, the equals, and not that. But what this stands for, when you write this, this is a position vector. It's more than a point. Do you get the point? Please look at the difference. A lot of you, when you get going fast on your homework and your test, you're going to start writing stuff like this, and you're going to imply that this is a vector, and this is not a vector. There's a subtle difference here. Please look at the difference. Is this a vector, or is this a point? What do you think? This is a point. This is mapped on the xy plane. You can actually get there, no problem. The thing that travels, that points you to, that has a length of the origin to that point. So get this straight. This is just a point. Just a point on the graph. The thing that goes from the origin to that specific point, that's what this means. That's the vector. Does that make sense? It has a lot more to it. It says there's a direction, there's a slope involved in going from the origin to that point. There is a magnitude, there's a length on how long we have to spend getting there. There's a lot more to it. So when you're writing down position vectors, we have this. When we're just talking about points, that's when we use the parentheses. Show of hands, you understand the difference there. You're going to make some mistakes on it. That's okay, but try to think about it when you're doing it. If I'm working with vectors, I need this. I can't have this. That's not a vector. If I'm working with points, don't give me that. It's just this. Now let's look a little bit deeper at just a second, and then we're going to move on. Notice how the numbers are going to be the same, though. Isn't that interesting? So if I want a position vector that goes to a point, take the exact same numbers and put a bracket around it, and you automatically get a position vector. I'm going to prove it to you in just a second. We're about ready. To start actually doing some vectors with this one statement right here. Any vector can be translated to a position vector. Let me show you how. We'll spend some time doing this. We'll talk about how we say the two vectors are equal. We'll talk about how to find magnitude. It's seriously really easy. You just got to learn it. You just got to see it once and you'll probably forget it. So any vector can be translated to position vector. Okay, how in the world do we do that? Well, here we go. So let's suppose two points are given. It's really easy to find a vector between 2 points, and you know what? The way we do it, it automatically gives us a position vector. Automatically. It's really easy. How? What do you think? How would you find a... What would you do? How would you take these 2 points and translate it to something that starts at the origin? What's the point for the origin? And still have the same length, the same direction, the same everything. What do you think? So basically, it's saying if I had, I'm gonna work with this one too. Let's say, leave yourself some space. I'm gonna fill this all out when we get here. Let's say that we had this. This vector W It started at 1, 2, and terminates at 6, 4. We got this other vector v that starts at the origin and terminates at 5, 2. Here's my first question to you. Are these both position vectors, yes or no? Come on, both position vectors, yes or no?
Yes.
Is one of them a position vector?
Yes.
If you don't understand what a position vector is, position vectors start at the origin.
Yes.
Are both of these position vectors?
No.
Nah, which one is?
The one starting at origin.
Yeah, one of the origin. Hey. Yeah. Well, here's how we translate them. If this is a vector, obviously it's going from one point to another point, just like what I'm showing you here. So suppose that we have 2 points. Here's one, here's another one. A vector between those 2 points, and we can already make it a position vector, is given by this. So the vector v, which goes from point 1 to point 2, here's how you do it. What do you think? Oh, well, I'm not really concerned about the length of it right now. I just want to move the vector. So, watch. If I want this thing to go from here to here, basically I want the same length here and the same length here. I want that movement, I just want it down here. Does that make sense? So, ultimately, I mean, when I'm looking at this, I start at 1 and I'm moving to 6. I don't want to start at 1, I want to start where? 0. If I start at 0, I'm not going to make it to 6 anymore. I'm going to make it to 5. How do I go 1, 6 and get 5? What would you do? You can speak in here. It's okay.
Subtract.
Subtract. This is basically saying, hey, according to the x-axis, you're starting at 1. I want to start at 1. I want to start at 0. You're ending at 6. Well, if I start at 0, I'm taking this distance here and saying let's not have that 1. Just subtract. So we're going to take our x2 minus x1. It's got to be in order. Please do that. And our y2 minus y1. How you find position vector every time between 2 points? It's really easy. You just subtract them, do it in order, and you're good to go. Head nod if you're okay with that one so far. Okay, we're going to come back to it. We're going to talk about these in a second. I want to give you a couple others before I go. We did talk about, we talked about direction. And when we're talking about the XY plane, direction means slope. So we're going to talk about slope a little bit. We also got to talk about length, that idea of magnitude. Let's talk about these things and then do some work with it. Now, I gave you a little triangle here, and if you remember anything about slope, slope is always rise over, that's right, always rise over run. But check this out. This is pretty cool. You know how to find the slope between it. Just watch. It's pretty intuitive. It's just a little weird. You got to wrap your head around it. You know how to find the slope between 2 points, right? What is it? y2 minus y1. y2 minus y1 over. Here's how you find the slope of any position vector ever. This number over that number, done. Why? Because you start at the origin. Because starting at the origin makes things really easy. Because if you start at the origin, the climb is automatically your rise. And the run, this way, the run is automatically your run. So when you have a position vector, it's easy. The slope is given to you, it's y over x. That's what's kind of nice about this. So y2 minus y1 over x2 minus x1, yeah. But it's this number over this number if you have a position vector. It's very nice. Done for you, basically. Bless you. Okay, and we'll talk about length. What was that word? Length? Come on. Good. We get a special symbol for magnitude of vectors. Magnitude is really just a vector idea. So we wouldn't say, hey, what's the magnitude of that scalar? It's already a number, right? So basically what we're doing with the magnitude of a vector is saying how long it is. What is the scalar of that vector? That's what we're trying to do here. So when we say magnitude, we have this notation for it. Whenever we're talking about the length of a vector or the magnitude of the vector, put the vector name, it has the vector symbol, and then we're going to put some absolute value, and then do it again. We're going to use this notation because most people use that notation. So when we talk, and I think it's going to go really well with your linear algebra class that you're probably in, because I think they use that magnitude in there also. So this is what magnitude is. This right here represents just the length, not the direction, but the length of whatever this vector's in. Show of hands if you're okay with the notation on it. Now here's how we do it. It's going to look really familiar. It's going to you're saying, wow, you're missing some numbers here, but then you'll think about it for a second. Here's what the magnitude of a vector is. Take the components. It's a new word for us. The components of a vector are these numbers. The x component, y, just like the x coordinate, y coordinate. X component, y component. Take those components. So take the component, square it. Take the other component, square it. Take square root. What's it look like to you left-siders? What's it look like? Is it the distance formula?
Yes.
Where's the missing numbers? Because usually distance formula is, you take out this number minus this number and you square it, and then this number. Remember that? Distance formula? But wait a second. What if we have a position vector? What's always the second point? Well, the first point, I guess. What's always the first point? So if I did the distance formula with any position vector, check this out. It'd be 5 minus 0. It'd be 2 minus 0. So when we're talking about magnitude, we love talking about position vectors because if one of those points is 0, it makes our lives easier. This is how we find magnitude. It's really easy. Take the numbers, square them, add them, square them. It's distance formula, but you always get 0, 0 for that initial point. It's really nice. Head nod if you're okay with what I'm talking about so far. Okay. Here's my next question. We'll do just a couple things here, and we'll move on. My next question is, are V and W equal? In order for vectors to be equal, they have to have two things. They got to have the same magnitude, they got to have the same slope, so basically same direction and going for the same amount of length here, the same magnitude. Are they the same length? What do you think about that?
Yes.
How would you tell? We could do the distance formula. Let's try that for right now. Let's find a couple things. Firstly, let's find the slope, and let's find the magnitude. So the slope of V, I want to know what the slope of W is. Then we'll talk about the magnitudes. We're doing this pretty quickly, but I do want your help with it. Slope of V, I told you there's a really nice way to do the slope of a position vector, which is what we have here. I'm going to erase this. It looks kind of bad. Position vector. What's the slope of vector V? Can you tell me what the slope is? How'd you get 2/5? It's rise over run. If we're starting at 0, that is the rise is 2, the run is 5, so 2/5. What about the slope of W? Can you do the same thing for the slope of W? Is it as easy with the slope of the vector W? What do you think? No, because you get another point, right? So if you're going to do the slope of W, you have to do the whole 4 minus 2 over 6 minus 1. And now it's not necessarily super hard, but it is more work. That's why we like dealing with position vectors, because slope is right, it slaps you in the face. I mean, it's literally the same numbers. 2, 5, 2, 5. Put the y over the x, done. That's the slope of any position vector. Head nod if you're with me on one part. Okay, that's important. Well, this is also 2, 5. Slopes are the same, at least they're headed in the same direction. Have we proved that they are equal yet? Now we also need the same magnitude, so let's do that. Can you, on your own right now, just on your own, take about 15 seconds, can you please find this for me? What do magnitudes always have in them? Always, anytime you do a magnitude, you're going to be having like this idea of three things put together. Look at the formula. What do magnitudes always? What are you always going to be doing with magnitudes? Are you ever going to be? Well, you tell me. What do they have? I'll give you one. They have a plus in them. You're always adding. And they got squares, and they got what else? If you're not taking a square root, you're not finding a magnitude. Okay, so when we find magnitudes, we got squares, pluses, and square roots. That's what we do with magnitudes and position vectors. So we're going to have 2 squared. You know, honestly, it doesn't even matter the order because we have that addition, but I said it backwards. We have 5 squared, we have 2 squared, and we do. Don't forget the square root, though. Please don't forget the square root. Did you guys do the same thing? Did you get square root of 29?
Yes.
Perfect.
Are those absolute value brackets you have for the vector?
They're real similar to absolute value. They look kind of like, and that's why I'm using these double absolute value. There's 2 of them right there, and that is the idea of the magnitude of the vector. And that's our notation for it. Yeah, just so that we don't get it confused with absolute value. Some books do have just one set, and they treat it the same, absolute value and magnitude, and you're supposed to know the difference. I like doing the 2, that way it's not ambiguous. You go, this is the magnitude of the vector, this is what we're talking about. How about the next one? Can I do this simple little work with vector, the magnitude of vector W? Come on now, can I do the same thing as, no, well, there's more numbers to it, so if you're doing this, you have to do the old traditional distance formula. We got 4, well, it's 5 minus, if I could write down what my head was thinking. 6 minus. You know, it's funny when you like see a number and then your head says, "No, I'm not going to write 1. I'm going to write 5 just because I like 5s right now. Forget you 1." Does it work out the same? Right here, this says, "Hey, same slope, same magnitude, these vectors are equal." And you can write that statement right down here. So we'd say vector V equals vector W. There's actually kind of a quicker way to do it. I'm going to show you that right now. It'll take like 5 seconds, and then we're going to get onto a little bit more pointed material, I'd say. There's another way you can do it from now on. Here you go. With me? Ready? If you ever want to check to see whether 2 vectors are identical, if they're the same and they're not both position vectors, because then it'll be really obvious, just find the position vector of both of them. So if I wanted to find out what the vector V really is as a position vector, please notice something. This is not a vector right now. That's a point. It's telling you what the terminal point is. Does that make sense? This is not a position vector. It's a point. It's telling you what the terminal point of that vector is. If you want to see whether 2 vectors are really equal, just find a position vector. So for instance, vector V says, hey, take 5 minus 0, take 2 minus 0. Put it in these brackets that say you're finding a position vector. This is how we find a vector between any 2 points. Take your x coordinates, subtract them. Take your y coordinates, subtract them from the terminal first to the initial second. So terminal, initial, and see what you got. What are you going to get? Is that a big shocking surprise? Guys, we talked about it, right? We said this. Position vector is really freaking easy because if you have a point, the terminal point always defines your position vector. All you gotta do is take the same numbers, just have that weird bracket saying you have a vector, and that's the idea. Show of hands feel okay with that one. How about the other one? Let's talk about W. What's the first number I'd write?
6
Minus?
1.
And? Do you end up getting the exact same thing?
Yes.
Notice how this point is not the same as that point because this is not starting at the origin. That's the whole idea here. Do you really get it? Yes, no, yes, no.
Yes.
Yeah. Okay. Let's go ahead. We're going to take our break and come back in 10. Welcome back. So, working with position vectors, here comes our practice, how you do the things that we need to do. These are very, very basic. No more drawing vectors on the page and then moving on. That we're going to do it all mathy-like now, and it's really straightforward. One of them you already know. So you know how to find the magnitude of any vector? Because we're talking about position vectors, it's really, really easy. Here's the recap. It's just a square root. We take the components of our vector, we square them, we add them, we take a square root. Yep, distance formula, it's just because one of your points is 0, 0, it's easy. If we want to add vectors together, now here's something that's really interesting. We knew that we could take vectors and put them end to end and add them, right? And go from starting spot to ultimate ending spot. Well, we can do that mathematically too. And it's really, really easy. If you want to add vectors together or subtract vectors from one another, just subtract the numbers, man. That's all we got to do. So if we're starting at A and if we're starting at the initial point of A and ending at the terminal point of B, and we want to add those vectors together, if we just add these component by component, that takes care of vector addition for us. It also takes care of vector subtraction for us. It's really straightforward. Add the components. Just make sure you don't screw up the components themselves, okay? So if we want to do vector A plus vector B, we can do A1 plus B1. We can do A2 plus B2. And then it gives us a new vector, and that's how we add vectors together mathematically. Very straightforward. Also, hey, we knew that we could grow a vector or shrink a vector by multiplying it by a scalar. Do you remember talking about that? Those numbers, just those numbers, like multiplying by 3. This right here, this scalar c, which I'm going to use to represent a scalar, if I wanted to multiply a scalar times a vector, all that happens here is that we take each component and multiply it by that scalar. And now we get to practice a couple of these things. So what I want to do right now is basically this is enough for you to go and do it. You could probably do it. Magnitude's really easy. It's easy to add. It's easy to subtract. It's easy to multiply. I want to give you at least one example to see that you guys can do it. Then we'll talk about unit vectors, and I'm going to talk a whole bunch about that and a special way to find unit vectors. So here we go. Example time. So let's say I started off with vector A and vector B. I want to find a couple things. Can we do it? Let's see. What's the number 2? What's that doing there? What would you call that if you had to say anything that's
Scalar.
Perfect. So scalar number 2 just times the vector A, whatever that is. What do you think it's going to be? So when we're multiplying a scalar times a vector, literally all it's saying is, hey, take every component here, multiply every component by 2. That's what we're talking about here. It says take the scalar, multiply every component by that scalar. So if I want to take the vector A and multiply it by the scalar 2, we're going to get -2, we're going to get 4, and that's what that vector is. -2 times, then that's extended the length twice. That's what's happening. Show hands if you're okay with that one. Okay. How about A plus B? Let's see if we can do that one. We'll write this one out for this one at least. If I wanted to add vector A plus vector B and not have to draw the picture because I don't want to do that anymore. I want to be able to do it mathematically. What's the first number I'm writing? Good. We add our x or our x components first, so our -1 or 3 first. Then we add our, what's the other ones? Just like the slope formula, it's really easy to screw up numbers in this. Just, man, mind your numbers. Just go slow enough so you're not making mistakes on it. It's really easy to make mistakes in this class because we deal with a lot of numbers. But we're kind of back to that, right? It's easy to screw those things up. Just go slow enough that you don't mess that up. Maybe you'll double check your work every once in a while. What are we going to get? You can say it louder, man, because the air conditioner's on everything. 2, 3. I'm going to do this one with you. I want you to do this one on your own here in just a second. I'll give you some time for that. Let's try A minus B. Notice with A minus B, graphically, we would have to switch around that A plus -B to make that vector go the other way. But when we're doing this just algebraically, it's even easier. Literally just subtract them, because we can do that with our numbers now. So if I wanted A minus B, this looks like -1 minus 3 and 2 minus 1. Make sure we're using our vector notation because these are changing to position vectors. I'm looking at -4, 1. Did you guys get the same thing? I got it. That's the idea. It's pretty straightforward. Do you think if I give you some problems like this, you could do them? Yeah. How about this one? Let's talk about it. Then I'm going to give you some time to do it on your own. Try this. What would you do first on this problem? Can you find a magnitude right now with this? I don't know. What do you think? Okay, so the whole idea here says, all right, well, I'm going to need to figure out, or condense that out, just like order operations. I'm going to need to figure out what this is. I'm going to need to know what 2a actually, well, I already have that. I'm going to need what plus b is. So I'd be taking basically this vector plus this vector, figuring out what that is, and then finding the magnitude of that. Does that make sense? Try it. I'll give you about 30 seconds, see if you can find the magnitude.
What is absolute?
Oh, yeah. My bad. Yeah, so it happens when you drink too much Absolute, right? I mean, wait. This is water, I swear. It's a joke, come on. Yeah, thanks for, you know what, when that happens, would you please catch me on that? Because how I grew up doing this was with just the one. I like the two better. I think it's less likely to have ambiguity. So when I make that mistake, catch me on it. You know, at this level, I don't care how fast you do this stuff. You want 13 steps or 1 step. I don't care. I really just want the right answer. Does that make sense? I don't care all the work you're showing me. I really don't. I need you to know how to get this vector and that vector. That's the money. That's what I want. So the 2a plus, if you can do the scalar number 2 times the vector a and add the b and do that all at once, great. I probably wouldn't try to do the magnitude all at once. That's not something I would want to do. What I would do is figure this guy out. So this vector, what is that vector when I take 2 times vector a plus b? What would you get? Yeah, it's really this plus that, 1, 5. That's a position vector. And then I'm going to take the magnitude of that position vector. Tell me simply how I take the magnitude of a position vector. How do we do it? Square it? Add it? Perfect. So the magnitude is going to be 1 squared plus 5 squared, square root. Looks like square root 26 to me. Did you guys get square root 26? Leave it. That's it. That's what I'm actually going to do. Now, the last 2 things we're going to talk about are unit vectors. We'll talk a little bit about it right now. I'll show you how to do it. It's very, very easy. We'll talk about a different way to describe vectors, very useful. I'm going to come back to unit vectors and show you something really kind of cool. With me? You don't even know yet. You will. You'll know. Unit vector. What's the word unit mean? Like in math, we talk about unit. What's? I mean, sometimes it means like miles or gallons or stuff, but we're talking like a unit vector. That idea unit vector says, and some of you guys raise your hands, and you're right, it has a certain length. A certain length, if I say unit, means 1. So a unit vector is simply a vector with a length of 1, or a magnitude of 1. Say what?
It's a unit circle.
Ooh, we're going to talk about that. That's the interesting part. A vector with a length or a magnitude of 1. You can change any vector into a unit vector. It's not hard to do. How would we do it? Let's say we had this vector and it was it had a magnitude of 3. How would I make the 3 into a 1? Divide by 3. What if I had a length of -5? What would I divide by? Yeah. Let's divide a vector by its magnitude, and it will always give you a unit vector. Does that make sense? If we take something that's 5 units long, divide by 5, it's going to be something 1 unit long. That's how unit vectors work. So unit vectors, very easy to find. Take a vector, divide by its magnitude, unit vector. To find the unit vector from any position vector. Divide by magnitude. I'm going to say it simply, just divide by magnitude. Of course, it's math, right? So I got to give you some notation. Let's talk about unit vectors. For us, we're going to use U to mean the unit vector. However, because it has a length of 1, because it's a kind of a special idea, there's a little bit more notation I'm going to put up here. When we're talking about unit vectors, we don't have this thing anymore, because that stands for a position vector. That's what that is. So when we're talking specifically about a unit vector, we say, you're so special, you get like a party hat, man. We're going to give it a party hat. We little hat up there. Give it this little arrow thing. Kind of like if you were ever in statistics, you had P hat, Q hat. That's what we have. It's that same symbol. This is what defines for us a unit vector. How we do it, it's super easy. You take whatever vector you're given. So let's say we had vector B. We divide by the magnitude of vector B. That's going to give us a unit vector. Now here's something that's also interesting. How about this? Hey, we still know how to do algebra. Could you solve this for that vector? Okay, the answer is yes. How do you solve this for that vector? What would you do? This says something. Every vector can be defined by a magnitude times a unit vector. Did you guys see it? A magnitude's a scalar. That's really interesting. This is kind of cool. It's really cool. It says that if I want any vector in the freaking world, all I need is a direction times a scalar. All I need is a direction times, and I can grow a unit vector into whatever vector I want. Does that make sense to you? And that's what this next thing is going to say. So if I solve this for vector v, we can define a vector as magnitude times direction, or magnitudes times a unit vector. So when we do it, we say, hey, let's just multiply. So we got vector v equals magnitude times direction. How I would like for you to think of a unit vector is direction. So when we have this unit vector, it's got a length of 1. That's kind of like our standard unit, right? It's saying that's our basic thing here. That's what I want you to think of is direction. So when we think unit vector, you think what? No. Okay. When I think unit vector, yeah, it's got a length of 1, but I want you to think direction. So word association here, people. Unit vector, direction. Let's try this again. Unit vector? Direction. Oh, you got it. Geniuses, all of you. That's right. Yeah, so unit vector means direction. It's giving us the direction of our vector. Are you understand what I'm talking about? It's kind of like saying this. It's saying, hey, I was traveling north at 60 miles an hour. Awesome. What direction did you travel? North. That's what a unit vector is. It's just giving us that direction, our heading, if you will. Are you with me what I'm talking about? The 60, we lose that magnitude. It's just now has a direction. That's it. We can't have a magnitude, well, we can have a magnitude of 0, but if we had a magnitude of 0, it wouldn't point us anywhere. Does that make sense? You gotta have at least something to say this is where you're headed. This is your direction. So we're gonna try just one of them. I just want to do one example here about how to find a unit vector. We'll talk about these things called standard basis vectors. Let's see where we're at there. So I want to find a unit vector. So here's what I'm saying, okay? If I say I want to find a unit vector, I want to find a vector in the same direction as this, but having a length of, how much? Come on, unit vector has a length of, 1. Perfect. I'm basically just looking for the direction of this vector. That's all I want. So let's try that. Name me the 2 things you need to figure out a unit vector. What do you need? You need a vector. We got a vector. And you need what else? Go ahead and find the magnitude right now. Can a magnitude ever be negative? That's why it looks like absolute value. It's giving us just a distance.
Yeah, distance can be negative.
I got 2. Did you get 2?
Yes.
That's awesome. Square it, add it, square root 2. Are we done? Is 2 the unit vector? No, 2 is the magnitude of this specific vector. Let's go ahead right now. Let's find the unit vector. So our unit vector says, all right, what we do now is we take the original vector and we literally just divide it. Notice what we're doing. We're dividing by 2. What is 2? Would you define it as a scalar or a vector? Can we divide by scalars?
Yes.
Can you multiply by scalars?
Yes.
So if we're dividing by 2, it's really multiplying by 1/2. We're just dividing this by 2. We're cutting the vector in half. It's the same exact thing. So what we have for our unit vector is negative square root of 3 over 2 and 1 over 2. I want to show of hands if you feel okay with that so far. You know, a lot of times, a lot of textbooks could also do this for you. Instead of just having this 2 in the vector itself, a lot of times they'll write it like this. They'll take that unit vector portion, the magnitude of it, and they'll write it out front, especially if it's a really nasty fraction. They'll write it out front, and they'll leave the original vector alone. And you can also write a unit vector that way. So, and you can kind of see it, right? It looks a little bit better even sometimes. It says, hey, here's your original vector, and I'm taking half of it. And that would give me the unit vector. Are you guys okay with this one? You sure? Any questions at all so far? first.
Still want to put the U in front equals.
Yeah, it's the same exact thing. It's the same unit vector, man. It's the same thing. It's just I'm choosing not to distribute the 1/2 or divide by 2 on both, or I'm choosing to. Neither one's much more better, all right? Same stuff. So this is a different way to write it, that's all. Other question?
Can we do an equity exam? Or do you want to-
Both the same. I don't care. Yeah, I don't care. As long as you know how to find a unit vector, I'm happy, man. If you can find a unit vector, that's good to go. What if I asked you this question? What if I wanted a unit vector in the opposite direction of V? Question. Is this going to be a whole lot more work than this one? What do you think? Let's talk about it. Unit vectors do this, right? Unit vectors take a vector and divide by the magnitude of whatever vector I'm working with. So, firstly, is the magnitude going to change for this vector? No matter what I do, is the magnitude going to change? Is the vector going to change? The vector itself. Well, if I want the opposite direction, okay, come on, put it all together. How do I find the opposite direction of a vector? Put a negative in front. Do you remember that V and negative V were the same kind of they're parallel, but they're opposite directions? Remember that? So if I ever wanted to find a unit vector in the opposite direction of V, here's a unit vector in the opposite direction of V. Do I have to recreate all of this work? The magnitude's not going to change, guys. The vector's not going to change. All this would be, our vector here, would be one of two choices. You can either have positive 3/2 -1, or even easier, just make it negative 1/2 and keep the same exact vector. Those would be the unit vectors in opposite direction. Hey, you know what? It's the same unit vector. It's just the opposite direction. Literally, that's the idea. Show of hands if I made this make sense to you. If you're okay. All right. Last thing, I think we'll start here next time. I want to talk about these things called standard basis vectors, and then we're gonna. Are you sure you're okay with the idea of a unit vector? Are you sure you're okay with that one? You okay with the notation, a little hat that we give it, and having fun? It's like a party. I mean, it's a math party. Have you guys ever had math parties? No? Losers. Math parties. That's where it's at. Don't have math parties. They're really lame. All right. I've been around, so you know. We're gonna talk about something called standard basis vectors. Listen, this is not different. It's not harder. It's just different. It's just a different way to talk about the same exact stuff that we have been talking about. Why? Because the math works out nicely when we get to vector functions. So it's a way for us to work with vectors a little bit nicer than having commas everywhere. So let me describe it for you. This is kind of I'll give you a proof on why it works. It's not hard, don't worry about it. But this is just a little bit extra. Normally I would just give it to you and we do some examples, but I want to show you where it comes from. So it's this, if you want to think about it, it's just a different way to represent position vectors than the stuff that I've already given you. Head nod if you're okay with that. It starts with these two ideas. I'm going to define for you two very, very specific vectors. I'm going to define for you a position vector that goes from the origin to 1, 0, and one that goes from the origin to 0, 1. Can you plot those vectors on XY plane? If you can right now, you understand what a position vector actually does. If you can't, then you do not understand what a position vector actually does. Can you plot these vectors? Can you show these on a graph? So let's get it all together, okay? Where's the terminal point of that vector? What's the end of it? Specifically. That's the initial point would be the origin because I'm talking about position vectors. What's the term? Come on, what's the terminal point? Some of you already said it, I just didn't say it loud enough. 1, 0. What's the terminal point here? 0. Are you guys getting the idea right now? That's why we drew them on the graph so you guys understand what a position vector does. Starts with the origin, goes to a point. What's the point? Right here. That's the point. It's a vector saying we start at the origin, but the point is, that's why it's so nice, because it inherently gives you the point. Do you get the point?
Yeah.
If I were to draw these, this vector goes from the origin to 1, 0. It is that vector. If I've done it right, 1, 0. This vector is the one that goes from the origin to 0, 1. It's that vector. Head nod if you're with me or not. That's what position vectors do. That's literally what these things stand for. Are you guys okay with this one? Now, come on, let's flesh this thing out a little bit. How long is that vector? How long is that vector? Would you say they're both unit vectors? Are they the same unit vector? If they were the same, they'd be going the same direction. Are they the same unit vector? No. So they're two different unit vectors. You with me? One of them's going along the x direction, one of them's going along the y direction. And that is the definition of what these two things are. I with a hat. Why am I giving it a hat? Why?
Unit.
Unit. And J. These two guys right here are the basis for how we can define vectors a different way. That's why they call standard basis vectors. This is our standard basis. It's what we start with. How we move in the x direction, how we move in the y direction. Well, hey, this would give us the... Hey, I told you how to think of unit vectors, right? When I say unit vector, you think, don't say one. When I say unit vector, you think direction. A unit vector gives a direction. This right here, this I, literally just means x direction. That's all it means. This direction here, what direction is that? That's what I want you to think of. When you think I, think x direction. It's a unit vector. Think x direction. When you think J, I want you to think, it's obviously a unit vector. Think y direction. And they look just like that. They're position vectors. Now here's a little proof for you about how we can define these position vectors just slightly differently. Let's start with this, just a vector v. Vector v has two components. It's got an x component and it's got a y component. Hey, that sounds pretty darn familiar here. By the way, if you don't want to write this down, I don't even care. I just want you to see where it comes from, all right? I could give this to you a lot easier to show you how to do it, but I want you to actually see what's going on here. Now check this out. I'm gonna kind of invent some vector addition here. I'm gonna create two vectors that are gonna separate this vector. So for instance, let's separate this vector into two different vectors, v1, 0, and 0, v2. True or false? If I add these, I will get this. We learned how to add. If I add these, I will get this. True or false? What do you think? Yeah, this plus 0 is obviously that 0 plus this is obviously that v2. It's the same exact thing. Basically what I'm doing here is going, hey, I got this vector. This is v. If I split this up into these two vectors, I get to the same spot. That's basically, I'm just taking the x direction with 0y and the y component with 0x. I'm just splitting up this vector, making a triangle out of it. That's all I'm doing. Head nod if you're with me on that one. But more than that, that right there, whatever that is a number. Are you with me on that one? It's just a number, like 2, 5, or 1/2. I don't care what it is, but it's just a number. If it's a number, It means it's a scalar. If it's a scalar, it means I can divide it out just like I could multiply it into a vector. So I'm going to do it. So this says I could do, if I divide out the V1, hey, what's V1 think factoring. I'm forcing this to factor out V1. What's V1 divided by V1? What's 0 divided by V1? Holy crap. Do you see it? Maybe not yet. I don't know. If I factor out the V2, it's a scalar. It's just a number. I can factor out scalars. I can multiply scalars from vectors. I get 0 and I get 1. Here's what it's doing. It's really a beautiful thing. It's very simple. It's kind of elegant, really. It's saying, hey, you know what? Instead of just thinking about going from here to here, let's think about vectors in a slightly different way. Instead of just going from here to here, let's think about them in terms of vectors that you would add in x direction and in y direction. Here's the x direction. Redefine this. What is the vector 1, 0? Come on. It's up. Plus something, a scalar times j. It's saying this. I can redefine any vector vector by taking its x component and saying, yeah, hey, look, if this is 1 unit long and I multiply it by a scalar, all I'm doing is growing my x direction. If I take this is 1 unit long, all I'm doing is growing my y direction if I multiply it by a scalar. It's just taking the x direction and the y direction and doing vector addition with it. That's all it's doing. Just a really different way to think about it. Show of hands if you understand that idea. It's very easy, very straightforward. I'm going to do one example with you, and then we're going to call it good. So the two ways, and they are universal. I do not care how you write it on the test. They're the same. If we're talking about a position vector, we have two ways to write it. We can either write it like this, with just components. A lot of people love this way, as long as you don't screw up parentheses versus those vector brackets, okay? This way, or if you want standard basis, it's the same stuff. Can you translate between this and this?
Yes.
Can you translate between this and this? One example, it's really easy, then I'll let you go. We're going to add to this next time, but this will get us started. First thing, could you give me the standard basis vector? So basically a different way to define this. Instead of having V as the vector with notation with the brackets, can you do standard basis? Right side, tell me what you would have for your x component. What is your x component? So I want to say in the x direction, I'm going 3. Does that make sense? So take the x direction, multiply it by 3. Very straightforward. Take the y direction and multiply it by, that's what you're doing. That's what you're doing here. You're just separating this vector that starts from the origin, and you can even think about how you get there. You even get to this point by going x positive 3, y negative 2. Does that make sense? Well, that's what this says. Go in the x direction positive 3 and the y direction negative 2. It's the same exact thing. That's the idea. Now, how about one more? Can you give me the slope right now in 5 seconds of that vector? What's the slope? Negative 2/3. No, that's the idea. Did it make sense today what we talked about?
Yes.
We're going to deal with this a little bit more. We'll end this section next time. All right, well, welcome back. Today is our time to really practice everything we know about vectors so far in 2D, and then take in our next section how to extrapolate this concept and go 3D with it. So right now we're just going to practice with these 3 vectors and find some of the main concepts that we really need to know. The first one is, can you translate them? Can you go between our vector bracket notation into our standard basis vectors? That was the stuff with the i's, the j's, and the k's. Remember, when you're switching back and forth, numbers don't change. It's literally, you take the x component, put an I. because the I meant, what did the I mean?
Direction.
It was a unit vector, right? In the x direction. Since unit vector means direction, it's just x direction. And then the j meant what direction? Right. And so basically what it does, it says, instead of thinking of this as a position vector from the origin to that specific point, it thinks of it as how would you get there along the x and then along the y and add them together, like adding vectors like we did before, okay? It's the same exact idea. So let's go ahead and do it. Left side, how about you guys? What's a different way using standard basis vectors that I could define A? Could you tell me? Perfect. So the 3, that's our x component. We put the I on it. So basically we take this, just this scalar number here, we attach a unit vector. This becomes the x portion of when we're adding those vectors together to get the 3, well, the 3, negative 2. And then, I'm sorry, you said one more thing. What was it? Where are you getting the minus from? Negative. Yeah, it's negative. I mean, it's pretty straightforward. So minus 2j. That's it. That's it. How about middle people, y'all? Tell me, how else could I write the vector b? What would I write that as?
9 minus 6j.
Yeah, fantastic. Everybody else on the right-hand side, y'all tell me how to write this one, please.
Negative 3.
Negative 3I
I
plus 1.
plus.
Do you need to write the
Or
1?
3 over. Because,
No.
You don't need to write the 1. It's just like having 1x. We don't write it. This stands for, and if you think about it, check this out. If you just cover this and make it 0, that literally is j. 0, 1. That is j. So 1j means the unit vector j. That's what it is. Show of hands feel okay with this so far. All right, fantastic. Can we go further? Could you right now, you should know, because it's super nice and easy, could you find the slopes for A, for B, and for C? Could you do it?
Yeah.
Let me give you about 10 seconds, about all this should be. Let's write the slope for vector A and B and C. How do you do it, firstly? How do you find the slopes for position vectors? What would you do? Since we have position vectors and our initial point is 0, 0, that whole rise of a run thing works really nice because it's literally given by here or here. And get used to finding slope from either one. They both work exactly the same. So, what'd you say again? Is it a 3 over negative 2 or negative 2 over 3? What would we do?
Negative 2 over 3.
Okay, just make sure you get in the right order. It's y over x, the y component over x. How about the slope for vector b? What is that one?
Negative 2 over 3.
You don't have to whisper it, man. I can't hear y'all.
Negative 2 over 3.
Wait a minute. What? What is it really?
Negative 6 over 7.
Should you? Let's talk about it. This is really what it is, right? Should you simplify it?
Yeah.
Can you simplify slopes? Slopes are a relationship among sides, so it's just a fraction. So anytime you get a slope, yeah, simplify. That's fine. Wow. Coincidence? I don't. Maybe. I don't. Let's do the next one. What's this? So here we got slope of A, slope of B, slope of vector C. What's this one?
Negative 2 over 3.
How'd you get that? What is it? How'd you start? What'd you put?
1 over negative 3.
We should know how to deal with some complex fractions here. We got 1 over negative 3 halves. That does not look like a great slope right now. So we're going to fix it, just like we fixed this one. If we, you know what, seriously, just move that to the numerator, move the negative up, and we get negative 2/3. What? That's crazy. Tell me something about all of these vectors. How do you know that they're parallel? We had a definition last time for same slope means parallel for vectors, just like it means parallel for lines, all right? Are they all equal vector? Are they equal to each other? What would you need to know?
Magnitude.
Okay, so right now, since we don't know the magnitude, we don't know if they're equal to each other, we're going to find that out in just a second, but we're not there yet. Right now, all we know is that they are parallel to each other. So all these vectors, A, B, and C, are parallel. A, B, C are parallel vectors. Can you please stop here real quick? I need to show you a different way to do this. I've mentioned it one time, but it's really, really important that you understand the second way to tell whether these vectors are parallel. It's the more used way. So this is really easy, right? Because the slope is when I taught it to you the first time. It's pretty easy. But there's a different way to tell whether 2 or 3 or 4 vectors or any number of vectors are parallel to each other. And the reason why we have the second way is because when you get to 3D, do you have slope in 3D? I don't know, we haven't made it there yet. But think about that right now. Slope on a whiteboard is really easy because you're climbing or you're falling or you're not. So you have positive or negative or 0. What about in 3D? How would we define slope going like this? But then we have to define a plane that way. What if it's not going that way? What's going this way? Then we have to find a new plane that way. And that's really weird to do. So instead of talking about slope with these 3D vectors, which is really hard to do unless we can define that plane, what we do is we do the second way of telling whether vectors are parallel. Here it is. We talked about it a little bit last time when I said, hey, you know what? Any vector, and there's a little side note here, can be defined as the magnitude of said vector times the unit vector in the direction of. Did you remember talking about that?
Yes.
I said, hey, find a unit vector in the same direction multiplied by the magnitude, and you have the vector. That was one of those definitions that we had last time. We're going to deal with that a lot in about 5 minutes. We'll do an example that covers everything, okay? But the idea is that magnitude is a scalar. Now listen, please listen. And look, and learn, all right? So let's say I had a unit vector, and I multiplied it by 5. Let's say I had a unit vector and multiplied it by 7. Let's say I had a unit vector and multiplied it by negative 3. True or false? No matter what, if I keep the same unit vector, I will get parallel vectors. What do you think?
True.
True or false? All vectors with the same unit vector are parallel.
True.
If we have the same, unit vector means direction, right? Parallel means in the same direction. That is how we're going to define parallel vectors also. So not just slope anymore, but if vectors have the same unit vector, they have to be parallel. Let's write that down, and then a corollary of that, one more statement, we're going to get that next. All parallel vectors have the same unit vector. But there's a little corollary here that I also want to know. These things suck. The corollary is if all parallel vectors have the same unit vector, then that means to really get different parallel vectors, I'm just multiplying a unit vector by a different freaking number. Does that make sense? Then if you think about it that way, all vectors that are scalar multiples are parallel. So basically, if you can define one vector as like 5 times another vector, they have to be parallel. Does that make sense to you? Here, watch. We'll do an example in a second. Here's the little corollary. Write it down. I'm going to show you. It's really easy. Once we do an example, you're going to wrap your head around it. But here's a statement that I'm going to make. Vectors are parallel if they are scalar multiples. That's what I'm going to make. And you go, I don't know what that means right now. What's a scalar?
Constant.
Yeah, it's a constant. It's a non-vector. Okay, so if here's what scalar multiple means. If you can take one vector and factor out a number, it becomes a multiple. If I can factor out a number such that I get that number times another vector, they are parallel. Let's watch. Let's look at A. I'm just going to write down A here real quick. And then let's consider B. B is 9, negative 6. I'm going to do this example, and then everything is going to click in your head, okay? Can you factor a number out of that? What number can you factor out of that?
3.
Let's do that. Notice, because we can multiply numbers into vectors, these scalars into vectors, we can also divide. Basically, you're multiplying by the fraction version of it. You're multiplying by, well, you're undoing that multiplication. So we factor out 3. Well, wait a second. That looks really familiar. What vector is that?
B.
A.
Oh, A, I'm sorry.
Just this one. What vector is that?
A.
So this is really 3 times A. I need a head nod if you're okay with just the factorization and noticing that this is literally a scalar 3 times a vector A. Hello, yes, no.
Yes.
Now let's put it together. What this mean? Look, hey, this is kind of cool. If you found the unit vector for this, the unit vector, which means you lose the 3. If you found the unit vector for this and the unit vector for this, would they be the same?
Yes.
Then they would be parallel. Here's what this says. It says, if you can tell me that one vector is just a scalar times another vector, they're automatically parallel. It's taking all of this stuff into account. All parallel vectors are the same unit vector. Yep, that means the same direction. Well, that also means that if vectors are parallel, they're going to be scalar multiples, because they're just going to be that unit vector times a different freaking number, okay? They should be longer or shorter, but they're the same direction. That's what this says. This vector is the same direction as A, it's just 3 times as long. That's what that's saying. Show of hands if you understand the concept there. It's a weird concept, but it's really useful. So right now when I say to you, find out whether vectors are parallel, there's 2 ways to do it on a plane. There's slope, which is easy, that's what I taught you first. But then there's also scalar multiples. It's still easy once you wrap your head around it. Just see if you can factor a number out. If you can, okay. And if they're the same, you got it. If you can't, then they're not. This method is what we have for 3D because we lose the slope for 3D. We're going to get there at the end of our day-to-day. Any questions at all, or is it making sense? Tell you what I want you to do. I want you to look at C. See if you maybe can factor something out of the vector C. Can you factor out negatives? Is that okay?
Yes.
Does that affect parallelity? I think I made that up. I don't even know. Look it up. If it's a new word, I trademark that. So parallelity. If you factor out negatives, does it affect 2 vectors being parallel? Okay, that was not rhetorical. If you factor out a negative, does it affect 2 vectors being parallel? No, it just would change the direction. Just go, but still parallel. So factor negatives, I don't care. How about fractions? Can we factor fractions? It's like double F words right there. Yeah, let's do that. So if we factor out, we got negative 3/2. If we force this to have a factor of negative 1/2, factor that, we get positive 3. Factor this, we get, let's see, 1 divided by negative 1/2. That's what factoring is, division. 1 divided by negative 1/2 is negative 2. Oh, I love it when this happens. That's A again. That's just negative 1/2 times the vector A. True or false? It's parallel. We already knew. We already knew from here, but that's a different way that you can look at it, and it's much more useful when you get 2 vectors in 3D. Have I made it make sense? Okay, we got one more big, oh yeah, I forgot the magnitudes. Can you do the magnitudes here? Okay, I'm going to give you about, do magnitudes of all 3. Would you do magnitudes, well, no, I'm not even ask the question. Do magnitudes of all 3 of these for me. I'm going to give you about 30 seconds to do it, okay? I'm just going to give you the answers when we're done with the 30 seconds. Try it. Did you find it? Right side, what you get for the, how do you do it though? I mean, really, how do you find the magnitude of vector A? Remember, position vectors are really, really nice. How do you find it? Square them, add them, square root them. That's what I want you to do for magnitude. Square them, add them, square root them. So here we have 9 plus 4 square root 13. For vector A, hopefully you got square root 13. Did you get that? For vector B, we got, let's see, that one, I got square root of 117. Did you get square root of 117?
Yes.
So when you square them, 81, 36, add them, 117, square root, don't forget square root though. That's the distance forming part of it, okay? Square root 117. The other one, a little bit nasty. When you do this, you get 9/4 plus 1, 9/4 plus 1, that's be 9/4 plus 4/4, 13/4. So if you got for magnitude of vector C, the square root of 13/4 would be square root of 13 over 2. That's probably what you would get in like the back of a book or something, okay? Because they do the square root of 4 and get 2. And not if you're okay with what we're talking about. Can you do it? Can you right now tell me whether two vectors are parallel in two different ways and be able to find magnitude? Yes, no? Yeah. Question.
Yeah, I was just wondering if we can actually tell if the magnitudes are the same just by pointing out the coefficient. Because isn't that what the...
Oh yeah, absolutely. So if you're like, well, wait a minute, are these the same vectors? No, because this is 3 times as long as that vector. They're clearly not the same. They're parallel. And if they're parallel and not the same length, then they can't possibly be the same. I do want you to know how to find magnitude, though, just independently. So right now, you could say they're not the same vector. They're not the same vectors. But this proves it both ways. Does it make sense? This is actually, well, when you look at it, half that vector. And it says it right there. It's half that vector. You can do it that way, too. Good question. Any other questions before we go on? You ready for the big time example that wraps it all up? Let's do this. This right here is like a major test typey question. Okay, a lot of people would put this on a test. A lot of people. I don't know. Maybe. Look, this man, it's got a lot of stuff in it. Okay, this really gets your understanding of parallel and magnitude and unit vectors. It gets it all going. So let's say that we got two vectors, A and B, and I want to find a different vector. I want to find a vector that has a magnitude of 3. I also want this vector to be parallel to the direction of this crazy vector that's 2 times A minus 3 times B. What in the world do we do first? What do you do?
What you point out there.
What do you do, man? We want something that's, okay, let's think about it. We want something that's parallel to this. Follow the thought process, because I know it's new. It's not hard, but it's new. It's weird because you have to think about it, okay? We want a vector. Don't start with magnitude. That's the last thing we're going to do. We want a vector that's parallel to another vector. How do you know when two vectors are parallel?
Same slope.
Same slope. Let's think more general.
Same unit vector.
Same
Unit vector.
that one. Two vectors are parallel. Oh my gosh. Two vectors are parallel when they have the same.
Unit vector.
Here's how this works. It's kind of a weird concept. We're going to find this vector right now. Is that going to be hard to do?
No.
That's 2 times A minus 3 times B. That's pretty easy. We're going to find this vector right now. We're going to find the unit vector. So basically, can we call this a different name? Let's find this. Let's call this W. What we're going to do is, here's the idea, and then we're going to do it. We got this vector called W. I don't know how it looks. I don't care how it looks. We got this vector called W. It's probably not a unit vector. If we want something parallel, please notice, parallel vectors have the same unit vector. So if you're ever asked, find a vector parallel to another one, you need a unit vector. Is that clear enough for you? Okay, so we need a unit vector. So what we're going to do is we're going to take this vector, whatever it is, we're going to shrink it down to a unit vector. Does that make sense? And then, once we have a unit vector in this direction, I want a magnitude of. So we're gonna take a vector, we're gonna shrink it to a unit vector, then we're gonna grow it back to the magnitude of v times our unit vector, and oh my gosh, that's exactly how we can define any vector like ever. Magnitude times unit vector. Now let's try it. The first thing, and you're going to do all of it, okay? I'm not going to do hardly any work right now. What I want you to do right now, so here's the idea. Find this vector. Shrink it, then grow it. Does that make sense? All parallel vectors have the same unit vector. Find the unit vector. So right now what I want you all to do, I'd like you to define W as this. Spend about a minute. I don't care how many steps it takes you, whether it's 1 or 50. Find W right now. Go for it. Man, nasty. If you're familiar with how to multiply scalars and then add and subtract vectors, what's going on is we're multiplying all of our components kind of independently, okay? So do your x components first, your I components. Do your i's. If you're not seeing your i's, then you're not seeing the problem very well. Don't lose your eyes. Get it? Get it? It's a joke. It's a Calc 3 joke. It's as good as it gets, okay? Stupid. So you take your 2 times negative 3. That's negative 6 minus 3 times I. So negative 6 minus negative 6i minus 3i. What do you get for that? I get negative 9i. Did you get negative 9i? Do you know what I'm talking about? So here's our vector A. 2 times this vector, that would give you negative 6 plus 8, negative 6i plus 8j. Are you following what I'm talking about? 3 times this guy gives us 3i plus 6j. Okay, well, then you can do it in your head, do as many steps as it takes, I don't care. But then we have 2 times this minus 3 times this is going to give you negative 9i. Then we have our j's. So the j's say, okay, we'll do exactly the same thing. 2 times 4 is 8, so we get 8 j's here, minus 3 times b, well that's minus 6 j's. How many j's do we got? So plus 2j. Okay, for real, show of hand if you know how to get that one. Good. Middle people, yes, no? You sure? Okay, true or false? That's a unit vector.
True. Also false. True.
If you're having to guess at it, why don't you find the unit vector and see? Because if you're right, it's going to be 1. Or, well, find the magnitude if you want. Find the magnitude if you want. And if you're right, it's going to be 1. If not, let's just try to find, because we got to do that for unit vector anyway, find the magnitude and try to find the unit vector from here. So the idea is, number 1, find this vector and then find the direction of this vector. I'll get you in a second. Find the direction of this vector. Everybody in the class right now, what does direction of a vector mean? What is the direction of a vector? It's a unit vector. Let's find the unit vector. Question.
I kind of like to look at it in the brackets. Would you want us to kind of convert it back to the I and the J?
No. You know what? I really don't care. I'm going to give you both brackets and the I's and J's because I want you to get used to it because you're going to see both of them. So sometimes I'm going to give it to you like this. Sometimes I'm going to give it to you. Sometimes I'm going to convert it just so you get really used to it. I like this too. I like it too. But this happens a lot when we get to vector functions. We deal with it. So we need to be used to both of them. Right now, I really want to know, can you get down to here on your own? Okay, now let's pause for a second. Let's do like a 20-second recap to make sure we're all on the same page, all right? Do you believe me that all parallel vectors have the same unit vector?
Yeah.
Okay, come on, focus. Do you believe me that all parallel vectors have the same unit vector?
Yes.
Yeah, same direction, okay? So if I want a vector parallel to this one, I want a vector with the same unit vector. Does that make sense? Your next step, I want you to find the unit vector for W. Do it now. Unit vector is pretty easy. You take the vector, whatever you're trying to find something parallel to, take the vector, divide by magnitude. So in our case, we got this vector, just find the magnitude, divide by it. I always like to do the magnitude just in the problem, so I'll write my vector, do the magnitude. Do you ever have to worry about negatives when you're finding magnitude? I don't even think about them. Just negative 9, who cares? You're squaring it. So we're going to get 81 plus, so altogether we'd have, show of hands if you're able to find square root of 85, if you're okay with it. That's fantastic. Do you know why we did it? Come on, put it together. Do you know why we just found the magnitude here? What are we trying to get to?
Unit vector.
Why are we trying to get to a unit vector? Why are we trying to get a unit vector right now?
Prove they're parallel.
I don't care. I don't need to prove something's parallel. I want to make something that is parallel. What do all parallel vectors have? So if you're ever asked to find a vector parallel to another one, you need its unit vector. Its essence, like where it's headed, and that's what a unit vector is. Is it starting to make sense to you? Josh, you with me? So now, a lot of times they do some pretty nasty things here with this format. So the unit vector can end up looking like this. Also, they're left rationalized, which means that you could end up looking like this. That's rationalized and put on each component. Do you guys see how to do it? That's rationalized, so it goes here, and it goes here, and it's rationalized. Another way, a much more better way, okay? When it's nasty like this, is to rationalize just this piece. And leave it out in front of the vector. And the beautiful thing, it's legal. You can even do it. That's how a lot of times we do that. And the reason why, trust me, when we get to chapter 12, and you deal with tangent, unit tangent norm, and unit normal, and binormal, these unit vectors get really nasty, and you're going to get a lot of this crap. Leave it up front. Okay, that way we're not distributing and then undoing it and then finding more unit stuff. It's a lot easier to deal with. Just leave it up front. That'd be my indication to you. So we're going to go through it one more time because I know a lot happened, and I want to make sure you're with me because if this is the capstone of this section. Okay, you got to get this. Do you understand why? First, did you understand how to find W on your own?
Yes.
Do you understand why we did a unit vector?
Yes.
Look up here for a second if you don't get it. Every vector, that's the V, can be written as a magnitude. Do you have a magnitude?
Yeah. Yes.
Do we have a unit vector?
Yes.
We do now. We didn't have one before. Does that make sense? So you can't just do this. You can't just go, hey, I found this one, let's multiply by 3. Well, that's not a unit vector. That would, stop and listen, that would create for you a parallel vector, but not one with that magnitude. I don't want to over-talk it, but I want to make sure that you guys get what I'm talking about. Did you get what I'm talking about? Okay, so we did this, awesome. We did a unit vector because I know that a vector parallel to this one is going to have the same unit vector as this. Same exact thing. And now we put it together. We go, okay, I want a vector that has a magnitude times the appropriate unit vector. Every vector can be defined this way. Since we have the unit vector and since we have the magnitude, it's literally just multiplying. So let's try it. Do we have that? What is it? What is it? Do we have, this is beautiful. Do we have the appropriate unit vector that we wanted?
Yes.
Yes.
Is it W?
No.
No. What is it?
U.
Yeah.
Yes.
You might see this written differently. If there's distribution going on, this thing's going to get pretty darn nasty in here. You get that negative 27 and you get that positive 6, square root 85 or 85 thing going on. Are you following what I'm talking about? You can start simplifying this if possible, but let's see, 8, 9, 10, 11, 12, 13. 13 is not divisible by 3, therefore 85 is not divisible by 3. If you know those tricks, that helps a lot too. So you just leave the 3 out front. This right here, and you can even see it. Look, you can see it. Look at that. What vector is this, please? Come on, everybody. What vector did you found it? What vector is this?
W.
Is this a number? It's a nasty one, but that's a scalar. A scalar times a vector gives you a parallel vector. This just happens to be a unit vector. Look what we did. Please look. We took this vector, we've shrunk it to a unit vector, and then we grew it back to a magnitude of 3. And that's exactly what I told you we were going to do. That's what we did. So it ends if this one made sense to you. Awesome. All right. We're going to talk a little more about unit vectors. Look, the word unit means length. It means direction. That's how we use it. But it means that it's this vector that has a length of, if this unit vector, which is inherently a position vectors start where?
Origin.
So if this vector starts at the origin and points somewhere and has a length of 1, it is going to be on the unit circle. Does that make sense? The unit circle has this radius of 1, centered at the origin. The unit vectors have to be on the unit circle. We can use that for a different definition of unit vectors. So provided we have this unit circle, a generic unit vector will have its terminal point on that unit circle. But wait, there's more. If we look at that trigonometric relationship here, and the angle that unit vector makes with the x-axis, well, that pretty much gives us a unit circle, right? I mean, that looks exactly like all this other unit circle stuff that we've seen before. But this is really interesting. We know a way to describe this height, and we know a way to describe this length. What describes the height on a unit circle? Sin. It's bad. Sine. It's not. You're not sinning. You're doing some sort of a side relationship on this right triangle we just created. That's sine theta for the side. Well, and this right here, this length right here up to here, this is cosine theta. But this is also pretty interesting. I'm going to kind of superimpose something on here. There's a little more to it. Because this is a unit circle, unit vectors have to be on it, but also these two specific unit vectors called I and J. Verify that for me. I and J also terminate on the unit circle. One's on the x direction, one's on the y direction. Does that make sense? Now look what it does. If I wanted to add, do you remember this, how we took this notation and we did the I, J notation by breaking up the vector and saying, instead of going from here to here, I want to do this and I want to do that. Do you remember that? This is what's going on. If this vector is I and cosine only goes to this part of it, cosine theta is a fraction of the I. Anytime you want to find a fraction of something, you multiply it. So if I want to add these vectors, if I want to do this one and this one, which we know we can, that's a horrible vector, I'm sorry. It's like I just had whatever. instead of doing this, my vector self, if I want to break this up and talk about it in I plus j, I'm taking a fraction of the I and a fraction of the j, and I can define my vector, instead of going from here to here, as this vector addition, our standard basis vectors. It's only this distance is that cosine fraction of it, that portion of it. I'm not going the whole way, right? I'm going only this part of it. I'm going only cosine theta of it. I'm not going the whole way. I'm only going sine theta of it. So instead of defining a unit vector as like a vector divided by its magnitude, if we know the angle that that vector makes with the x-axis, we can define it this way. It's not hard. I just need to give you the theory behind it. It's take the I direction and take cosine theta of it. I want to say cosine theta of it because cosine theta, you know this, right? Cosine theta maxes out at what value? 1. So if the angle is anything but 0, then we have a different value for cosine, and it's less than 1. So when we climb up like this, cosine starts shrinking. Cosine theta starts shrinking. I'm taking a fraction of I. Cosine theta gives it, cosine theta I, and I'm kind of ran out of room there. Cosine theta times I gives us the fraction of I that this vector has in x direction. That's what that's giving us. Does that make sense? This vector, this little guy, is cosine theta times I. Remember doing the unit vector and multiplying by a scalar to give it a certain length? We're now kind of taking a unit vector and multiplying by a fraction that's less than 1. It's shrinking it. It's shrinking it. That's what's happening. Plus, and we know by vector addition we can take one vector and add another one to it, and it equals this original vector. Sine theta j. That's another way that we can define a unit vector. If we know what?
The angle.
Gotta know the angle. That's the key thing. If you don't know the angle, then you, but if you do, then that's really, really nice. Because we start defining unit vectors easier knowing the angle. Show of hands if you feel okay with that idea. Did you get the whole idea of cosine cuts this unit vector down a little bit? Cosine times it, it's less than 1. It's gonna shrink it. It's gonna shrink it down to where that angle tells it to be. And sine theta does the same thing with our j. That's what this is doing. With me?
Yeah.
It's kind of cool, right? Interesting. Yeah.
That one correlates to
I can't hear you.
what you're showing on the right side of the board. Does that correlate with the problem on the left side of the board?
It's gonna. Yep, but you gotta wait for it. I want to do one as a transition from here to here, okay? Just a very simple one. What I want to do right now is I want to see if you guys can do this with me. Let's find a vector v such that v has a length of 9 and v makes an angle of pi over 6 with the x-axis. If you have not caught on to this yet, the things that we need to know right now are that in order to find a specific vector, like starting from scratch, like to invent one, you need a couple things. You need a direction and you need a magnitude. That is literally what defines a vector, direction and magnitude. Where you're headed and the length upon which you're heading. Does that make sense? So, well, a direction. What's a direction? What's a direction?
Unit vector.
Come on, everybody. What's a direction?
Unit vector.
So, if a vector needs a magnitude and a direction, are you given a magnitude up here?
Yes.
Yes.
What's the magnitude?
The line of
Good. That's easy. Okay, magnitude is given. Are you given a direction?
Yes.
Kind of. Are you given it explicitly?
No.
Can you find it?
Yes.
That's why we have this. Because when I say, hey, you know what, find me a vector that's in the direction of pi over 6. Pi over 6, what do you mean pi over 6? That's not a given vector already. That's starting from scratch from an angle. Well, now we can actually do it. Let's go ahead right now. I'd like to see if you can do it. So notice that this theta is from the x-axis. That's what I'm giving you, so it's really straightforward. I want to see if you can find a unit vector that gives me a direction pi over 6 from the x-axis. Can you do that? Let's try it. Do you guys have tattoos yet? Well, you're math majors and sciencey majors, right? You should have tattoos. The first tattoo I ever got? No. Unit circle. Right here. Boom. Unit circle. That's what I do. I'm not going to ever take my shirt off, so you'll never be able to prove me wrong. You should do it, though. Get it. Like, it's awesome. Like, wait, let me expand that unit circle. What? Okay. Or just like backwards on your forehead. Even better. That way you can see in the mirror. Do it. I dare you. I'll give you an A.
Right here? Right.
I'm lying. Look, I got this.
This is caught on video, right?
Yeah, I know, right? I'm lying. I'm editing that out. All right, let's go. Okay, back to work. Sorry, we're having fun. Too much fun. I know it's math class. Fun ends. More math. Look, if you want to find a unit vector and I give you an angle with the x-axis, make sure it's an angle with the darn x-axis. Got to be the x-axis. That's the way this works, okay? If I give an angle from here, this doesn't work. You have to subtract 90 minus the angle and get the complementary angle with that, okay? So be careful. With us, though, I say, okay, how do you find a unit vector that has this angle with the x-axis? Cosine of that angle, and then do I. Sine of that angle, and then do j. Listen, I'm really trying not to make it, I did all this theory behind it so you'd understand it, but I'm trying not to make it hard. Please look. Just watch. Cosine is always x, right? X, put them together. Sine is always y, right? Y direction, put them together. You're taking a fraction of the x direction, a fraction of the y direction, and you're adding them up. That's creating a unit vector for you. How much is cosine of, you need to know it, cosine of pi over 6, and don't give me decimal ever.
33.2.
Is that the vector I'm looking for?
No.
Is that the direction of the vector I'm looking for?
Yes.
Aha. So since vectors equal a magnitude, we've seen this enough times, times a unit vector, a direction, magnitude times direction, then our vector is what number? What's our magnitude?
9.
Times the direction we already had. That's the vector. Here's the unit vector times the magnitude, and that's what I'm looking. Could you distribute that?
Yes.
If you wanted to. You want to see something crazy though? Watch this. I mean, it should be kind of trivial, kind of obvious, but let's say we didn't use standard basis form. Let's say we use just like vector brackets. What's the first thing? Whoa, don't do that. That's literally a unit circle, point by point, a unit circle. Vector points to everything on the unit circle. Proof. Done. Cool, right? Let's use it. Let's use it with this. This problem is going to take us a while. It's going to take us about 20 minutes, all right? We're also going to talk about something right after that. It's very fast. I'm just going to briefly mention it. But this is the big deal, okay? This has a lot of work in it. For all you physicsy people, this is kind of for you. Let's say that I give you this scenario. We got this 2-pound weight, like a toy, hanging from 2 cables. And it weighs 2 pounds, and gravity's pulling it directly down, which means that we have these tensions on these cables that are holding it up. And the only thing I know right now is that this right here is 60 degrees. And this right here is 30 degrees. And our goal is to find these vectors. Find these vectors. Does that make sense? Find the vectors. Okay. I gave up on this problem when I was in calculus. I was like, nah, word problems. But you guys are here, so we're going to do it, right? Tell me something about forces. So we have forces and forces.
You have your normal force, and you have the force pushing upward, and you also have gravity pushing down.
Tell me something about that.
Forces are equal there.
They got to be equal. They got to be opposite. So what I know right off the bat is that this force has to equal the sum of these forces, some of these vectors basically, but in the opposite direction. Does that make sense to you? Pretty common sense, but it's what we start with. Okay, well that's nice. What we're going to spend a whole lot of time on is learning how to define these vectors by looking at a stupid picture like that, because it's very confusing. And then after that, a whole lot of algebra. That's the goal. So let's start with one thing. This is some advice I would always give to you. Wherever you have an angle, would you please draw yourself your own independent like XY axis right around that? So for instance, like right here, I would draw an XY axis so I can better define the way that angle is working. Does that make sense to you? And here, I do the same thing here. And even down here, even though this one's going to be pretty easy, I draw an XY axis, and that's going to help us with our angles, because otherwise we're going to get we might make our, whatever we're going to do with this, we might choose the wrong angle to do. So I want to show you how to do that, okay? So let's start with our W, and let's try to define our W. Firstly, what angle, remember, with what axis? What axis are we basing all of this stuff on? X. That's where we got this from. The positive X or the negative X? Yeah, that one. The one that goes this way. So really, this angle, it's the one that does this. It's the one that does that. Tell me, left-siders, what is that angle?
That's positive.
Say that again. Let's do it in radians, okay? Because unit circle works really well in radians, and I heard it from a couple of you. It's that 3 pi over 2. So from here we have 1 pi, 2 pi, 3 pi over 2. Head nod if you're okay that is the angle 3 pi over 2. This is why you draw an XY axis on all these things, because otherwise it's really hard to consider them if you don't do that. Does that make sense? So what I know, I know that vectors are a magnitude times a direct. I'm not going to write it again. Magnitude times a direction. Tell me, everybody in class right now, what's the magnitude of the W?
3 pi over 2.
Magnitude. How much is pulling down? Magnitude would be the weight pulling down. How much is pulling down? 2 pounds. Okay, so this is the magnitude of that vector. The unit vector just gives us that direction. Does that make sense? The way we've defined this, by the way, if you're like, what should it be? Should it be -2? Well, if you do, you got to change that sign. So what we're doing is saying, let's just look at the overall, let's consider it 2 down, and then it's going to be negative of the 2 vectors going up. There's other ways to do it. This is just the best way that I like. Does that make sense to you? It's the way I like. So what I want to know is you understand that this is 2 pounds pulling downward. So we have that magnitude of 2. How about the unit vector? So vectors are magnitudes times unit vectors. Let's do it. All we got to do is, you're going to do the next one, okay? All we got to do is figure out what angle we've made, take cosine of the angle I, sine of the angle J. Let's try that. What angle did we make with the x-axis? So cosine 3 pi over 2i plus sine 3 pi over 2j. I really gotta know if I'm making sense to you. Am I?
Yes.
Can you simplify the 3 pi over 2, cosine 3 pi over 2 and sine 3 pi over 2?
Yes.
I can. Can you guys do it?
Yeah.
What's cosine of 3 pi over 2? Do you know it?
Zero.
Interesting. That should make sense. Look at it. It's like, this whole thing is 0. What's sine of 3 pi over 2?
Negative
Negative what?
1.
Okay. So wait a second. So you're telling me that I get what? Now, let's see if that fits with what we have just done. Does it make sense that this vector is going directly downward on the y-axis with 2 pounds? The magnitudes can't be negative. They're always freaking positive, okay? That's why you don't put the negative here. And you don't do that. It's getting taken care of in your vector, provided you have defined it correctly. Does that make sense? So this says, hey, look, it's not going left, it's not going right, it's literally going straight down, 2 pounds, y direction, negative, done. Make sense? Let's define our T1 and our T2, and then we're going to pull this stuff together, do a whole lot of algebra, and we'll call it good. I might leave some of the algebra to you for the sake of time, but I want at least the setup. Does that make sense? The setup is very important here. So let's do vector T1. What do all vectors, like ever, have? What do they have? Magnitude. And?
Direction.
Great, let's start. What's the magnitude of T1? Folks, that is literally the question, right? I don't know. That's literally the question. It's the magnitude of T1. I don't know what it is. It's the magnitude. Let's leave it. That's your variable. It's the magnitude of T1. Leave yourself some space here, please. I'm gonna blow your minds here in just a minute, okay? But it's very interesting. Just wait for it. Now, the rough part. You got to understand what's happening here. This is why we draw our XY axes. What angle is this? Because it ain't 60. If you put 60, you were going to get this problem wrong. Because 60 degrees means this. Does that make sense? So from here, we'd go that way. That's the angle that I want. Yeah, 300 degrees, or can you do that in pies? How much?
5 pi or
I think so. 60 degrees is pi over 3. So 1, 2, 3, 4, 5 pi over 3. So if I wanted to find the unit vector that does this thing, please watch carefully. Please watch, don't miss this. The unit vector that describes from here to here is cosine 5 pi over 3i plus sine 5 pi over 3j. I know I'm kind of bending your heads a little bit here, but do you understand that we don't know the magnitude, so we're going to leave it magnitude T1? And do you understand that this angle right now is 300 degrees if we have this XY axis, or it's 5 pi over 3? Do you understand that idea? Do you also understand that if this is where my origin is, the vector I just described goes from here to here? Does that make sense? But wait, I want one to go from here to here. How do I fix it? Negative. Yeah. Do you understand where the negative's coming from? If we define our XY axis right here, our vector goes this way, go, no, let's switch it. Let's switch it around. There are other ways to do it. There are other ways to do it. You can define your vector here and use this angle, but you have to use some like alternate interior angle stuff, and you do that too. That's okay. As long as you're drawing yourself an XY axis and using the correct measurement from the X axis. Does that make sense? There's other ways to do it. I'll give you just one.
You couldn't rotate it in the negative direction?
Yeah, you can. If you did negative pi over 3, then it's the same thing, right? But you still have to have negative because that's moving our force back that way. Does that make sense? So yeah, negative pi over 3, that's okay. I like positive angles because that's how I roll. But around my unit circle, what? No, it's too late for that? Okay, whatever. Now the last one. Okay, come on, put it all together. what does every vector ever have? There's two things. What do they have?
Magnitude.
What's the magnitude? Yeah, we don't know. What's the direction? Oh, we gotta figure that out. Starting from here, we're going to here. Starting from there, think 5 or 6s, because that's what 30 degrees is. 7, 5, or 6. Because we got 1, 2, 3, 4, 5, 6, 7. Oh, we're almost there. Come on, we're almost there. What else? Why?
It's gonna be opposite.
Because if I did it this way, then this vector's going from here to here, and I want to flip it from here to here. Can you simplify these vectors here real quick, by the way? Instead of having cosine 5/3, because it's really awkward to work with, let's do that. Do you know what cosine of 5/3 is? Your silence is disheartening, my friends. Disheartening. I can't wait. Let's do it.
It's negative half.
1 half. Positive.
I don't know. You're supposed to know.
It's positive 1 half.
Is it negative half?
Good first.
Do you know what sine of 5/3 is? It's probably the other one, and probably negative. Huh?
Negative square root of 3/2.
Oh, it's this. Yeah. How about cosine of 7, 5, or 6? You know that one. All students take. They're both negative. That's the one. Switch it. Negative. Yeah. All students take, that means sine and cosine are both negative in this like semi-quadrant thing, okay? So they're both negative. It's important to get that down. Still with me? Okay. Now, we also had this little statement that we're going to fill out. What I'm going to do right now is I'm going to put these things equal. I'm going to give you the next step. And I'm going to give you the answer. Yes, you're going to have to do some of it on your own. We have covered all the hard stuff. This is all the hard stuff. The rest of it is algebra. It's a system of equations, and you're going to get it. But I want to show you at least this setup. So here we go. Once we've identified W and T1 and T2, and we've kind of simplified these things, let's put this stuff in this place. I'm going to work a little quickly here, that way we're going to get going on some time. But this W is our negative 2J equals negative. T1 is this negative, then lots of negatives flying around. Probably might be a better way to do it without a lot of negatives. You can work on that if you'd like. Probably number one thing I do is this right here. Just get rid of those two negatives because they're really annoying. After that, we're going to have to group a couple things. We're going to have to group our I's. We're going to have to group our J's, which means that, you remember that one time when we kind of don't like to distribute the magnitude into a unit vector? And sometimes we have to. This is one of the have-tos. because we have to group them, we're going to have to do vector addition, which means we're going to have to add our i's and our j's and set them equal to this vector over here. We're going to have to do that. So what we're going to do is distribute this magnitude right here. We'll get our negative t1 over 2i. It's going to get nasty, and there's nothing you can do to avoid it. This distributes, we get negative magnitude t1 over 2 plus this thing, j, plus magnitude I plus magnitude super fun. Awesome. Oh, that sucks. That's nasty. Can you follow the algebra? Can you follow the distribution? There's a lot of sign changes going on. I'm going to pause real quick to make sure I didn't make a sign error here too. It happens. It happens a lot. I'm good. Can you follow it? Could you do it? I think you can. I'm going to say it's just algebra a lot. Trust me, the just algebra is the hardest part of this class. Yeah, that's what you need to worry about, for real. It's just algebra. It's the hardest part. Now, let's think about it. What I know is that this vector, this is one vector, okay? We just haven't added it. This vector has to be equal to this vector. Does that make sense? Please listen carefully. This is the whole punchline. How many i's are over here?
None.
What's math for none?
0.
0 has to equal these i's. Did you get it? These i's have to equal 0. They have to, because there's none over here. So when I add these up together, this number, I know there's no i's over here, but look at why there's no i's. There's 0 i's over here. When I add these i's, I need to get a scalar, that number, that scalar of 0. These two things have to add to 0. And now if you're okay with that one. Okay. How much do these two things have to add to? 2. You got it. This right here is nasty, but it is a system of equations. Number one thing you're doing right here, multiply everything by 2. Please multiply everything by 2. Get rid of your fractions. Now I know that y'all aren't exactly used to dealing with systems of equations with square roots in them, but the same things apply. Same stuff. Here's how to solve the rest of the problem. We're going to end up running out of time a little bit, and I want to talk about one more thing before we do, okay? Here's the rest of the problem. You would multiply this by the square root of 3, and thereby get the same coefficient here. Square root of 3 times square root of 3 gives you that 3, which is actually kind of nice. Does that make sense? When you do this, these two things are going to eliminate. Do you see it? This is going to, okay, you're going to subtract them. This is going to give you 3 of these minus 1 of these. 2 magnitude equals 4. That's what that is going to give you. Oh, wait. Sorry. 3, 1. I missed something. Where's my negative at? Okay. Could have caught me on the negative like 5 seconds ago. Goodness gracious. Okay. Negative. Did you catch me that I missed the negative?
Yes.
Okay, missed the negative. Next time, say something, all right? So I don't look like a freaking idiot. Thanks a lot. Appreciate that. I still grade you. Yeah. Negative, which means that you're going to add these systems together. That's why I made my mistake next. So if I have square root of 3 and it's negative, and square root of 3 and it's positive, add them 0. This, when I distribute this, is going to give me positive 3. When I add them, I get 3 plus 1 is 4. The magnitude here is 1. Are you following what I'm talking about? That's why we write the stuff down. So when you go back over here, it's easy. You go, hey, what's this magnitude? Come on. 1. Take the negative, distribute. This is your vector. This is what T2 is. That's kind of cool, right? Done. The other one, how would you find out the magnitude of T1? How would you do that? Substitute. Any one of them. I would probably pick this one because it looks easy. So if I do that one, I subtract 1, divide by the square root of 3, and I'll have the magnitude of the vector T1. That magnitude is square root of 3. The reason why you get square root of 3 is because you get 3 over square root of 3, and you rationalize. You get that 3 root 3 over 3, and 3's cancel, and you get the square root of 3. So, okay, come on now. Put it together. What are you going to do with that one to tell me the vector? Where would you put it? You're pointing. Say it. Where would you put it? That's why we define it. So once you find this number, if you put it probably here, that looks nice. Just put the square root of 3 here and distribute it. And then we get negative square root of 3 over 2i plus 3 over 2j. And those are your two vectors. Show of hands you feel okay with that one. I know it's a lot. That's why it's extra. That's why it's some good stuff. But that's it for that example. I'm going to give you one more. I told you there was one more thing I want to talk about, then we're good to go. This is seriously just a little blurb. I promised you I would talk about how like airplanes and stuff fly through the sky and how wind affects them if they're on a plane, not climbing, not falling, just a constant wind, which is kind of simplistic, but that's all we can do right now. If you're ever given like a plane and a wind, that's a weird plane. That's a plane. A plane vector and a wind vector. Normally, this is not going to be to scale, normally we measure angles in like the real world from north, because that's our magnetic compass tells us north. So let's say that this is what I have. That's 45 degrees, and the wind vector is 75 degrees from north. Could you describe for me the plane vector and the wind vector if the plane is traveling at 500 miles per hour and the wind is 80 miles an hour? Could you do it? Vectors have two things. Come on, everybody. What's the two things vectors have? Good. What's the magnitude of our plane? Very good. So our plane would be 500 times a vector with an angle in it. That's a unit vector. But wait a minute. Okay, so I know which one's going to come first, cosine or sine? Cosine of, you got it, plus sine of 45 degrees. We'll use that for now because we're short on time. Well, I said 8. I meant 80. Wind, come on, quickly, magnitude. Cosine comes first. Cosine of? No. Not cosine of 75. Why not? Why not cosine of 75? Come on, why not? Because it's from the x-axis. So when we're doing this, Even though we measure in the real world by north, math measures from here. This is 15 degrees. Did you catch that? You were right on the 45 because it's right in the middle. That's why I did it. Tricky. 15 degrees I plus sine 15 degrees J. We're going to talk about the rest. If I said, okay, this is the plane, this is the wind, can you find the true course? The true course is... Oh, wow. No? It's the U one, right?
Yeah.
The true course is vector addition. That's where the plane's really going. If you have your heading, but your wind's blowing you, you're not going to know. You're not going to know when you're in the air. The wind's blowing you. You're still going this way, but the wind's blowing you. That's where you're really going. It's vector addition. That's what that is. If you wanted to find your ground speed, let's think about that. Speed does not have a direction to it. Speed is and it's how fast you're really going. Ground speed, therefore, would be the magnitude of where you're really going. That's how fast you're going according to the ground. Does that make sense? What's your heading?
Unit vector.
Where you're going divided by how fast you're getting there. That's your heading. And that's how this stuff can be used in a very simplistic way when we're talking about vectors and things. This, by the way, though, this would be the heading from the east. So it would be the heading from this way, not from the north. From the north, you'd have to take 90 minus it. That's the whole shebang. Did I make it make sense for you?